In the previous class, we were discussing about the electrocyclic reaction, one of the important class of pericyclic reactions, right. We understood how an alkene system either on photolysis or on thermolysis undergoes a cyclization to form a cyclic system, right. And then what we did is that we then went a little bit inner and we studied that this type of cyclizations are highly stereospecific. That means their cyclization takes place in two types of modes, right. One, it is con rotation, another by disrotations. Con rotation, we have seen that it should be both clockwise or it should be either anti-clockwise, but both should be in the same direction. In this rotatory, we found that one should be clockwise and another should be anti-clockwise, the orbital cyclization. So far we understood that part, and then later we went to this Woodward Hoffmann rule, where we studied that. I will just to freshen you up, we studied Woodward Hoffmann rule. Okay. So, what we studied, you have to consider your electron system of the given alkene, then your mode of reaction, then you say that whether it is allowed in thermal or photolysis. So, first we said that if it is a 4N system, okay, if it is a 4N system, then it undergoes a con type of cyclization, okay, and it is allowed only in heating, it is not allowed under photolysis condition. Same way for 4N system, if you are looking for a dis mode of rotation, then it is not allowed thermally, it is allowed under photolysis. If you go for 4N plus 2 system, it is just the reverse one. So, for con thermally it is not allowed and photolysis it is allowed. For 4N plus 2 system, that is for dis mode, it is other way round. So, up to this we studied in the previous class. So, this is the Woodward Hoffmann rule, where we said that this we formulated a rule where for 4N system under thermal condition it is con rotation allowed, under photolysis dis rotation is allowed, for 4N plus 2 under photolysis con is allowed, and under thermolysis dis is allowed. Now, what we will do is that we will take this, we will use this formulae, okay, rule, and then we will do it for some systems. Okay. First, we will take it for a 4 electron system. We will consider 4 electron system. Okay. So, we will take type of butadiene, since now you know about what is con rotation and dis rotation, I does not need to explain you further. So, just it does not need to put the orbital, now you know by heart. So, on heating, so what the rule says. So, what system it is? It is a 4N system. So, 4N system, what you studied on heating, it should be con. So, this is a 4N system. So, I am going to heat. So, it should be a con rotation. So, con rotation, the sign should be the con rotation. So, both should be either clockwise or anti-clockwise. So, this is both are clockwise. So, you get a cyclic product nicely. So, this is the interesting part, you get only one specific product. So, you get your hydrogen up and your methyl down. So, this is cis product. So, you get only cis. So, if I do this same chemistry, okay, under photolysis, then what will happen? For example, I take the same molecule, same diene system, I am taking the same dyne system. So, it is ZE, I am taking the system, I am just taking the similar system. Now, instead of heating, I say I am going to shine light on this compound. That means, I am going to photolyze this compound. Now, what happens under photolysis? So, what your Woodward Hoffmann rule says, if it is a 4 electron system, okay, 4n system, so on photolysis which is allowed? Yes, yeah, this rotatory. So, this is allowed. So, in this both should be, one should be clockwise, another should be anti-clockwise, right. Now, if you, so the hydrogen goes up, methyl, this side methyl comes up and hydrogen. So, what product you are getting? So, this side hydrogen gets up, you have a methyl down, this side you have a methyl up and you have hydrogen and you have a double bond. So, what is this? It is a trans. See, I have taken the ZE butadiene type of system, okay, a dyne system, okay, it is 1, 2, 3, so it is a hexa. So, if I do on heating, I get a cis product, but same dyne system, if I photolyze, you see I am getting the trans product. So, that is what the interesting part of electrocyclic reaction, it is more about the specificity, okay. One these conditions like heating and light, these are very important, okay. This is for 4 electron system. For example, if I take ZZ, okay, here it is ZE, if I take ZZ, what will happen? Same compound, okay, I am taking so I am taking ZZ system, okay. Now, what will happen? If I heat this, again the system is 4 electron, okay, that is 4n rule. So, you know heating it gives con. So, you know the direct, so what will happen? So, what product you are getting now? So, your hydrogen is up, methyl, in this case your methyl is up and hydrogen. So, you get trans. So, previous case what happened? If you are taken ZE, so you are taken ZE and you did heating and con, what product you got? You got cis, right. This time I have taken the same dyne system, but it is ZZ and heating undergoes a con rotation to give me trans product, just the reverse of what you got in the earlier case. Same way, if you take this ZZ system, Z and do the photolysis, it will be this, fine, but your product will be cis in this case. So, your hydrogen will be up, methyl goes down, this case also methyl goes down. So, you get a cis product. See, just if you take both ZE and ZZ, now you can understand that how important is this cyclization, and they are very specific, okay. If you take ZE and you heat it, you get cis, you take ZE and you photolyze, you get trans, but in other way around, if you take ZZ and heat, you get trans and other way cis. So, they are very specific and it gives only to the specific product. That is why the whole electrocyclic reactions are very important, because they are highly stereospecific, you get a very specific products, clear. Okay. So, now we have seen this 4 electron system. Shall we move to 6 electron system and see what happens there? So, we are taking 6 electron system. I have a methyl here and hydrogen. So, I have ene. So, now I do the thermolysis of this starting material. Now, tell me what it will be, what closure it will be, whether it is a con rotatory or it should be a dis rotatory. First, you have to understand what system it is. It is a not a 4n, it is a 4n plus 2 electron system. So, for 4n plus 2 electron system on heating gives you what? What mode it should? Woodward Hoffmann rule, what it says? Yes, it is dis. See, for 4n system on heating it is con. For 4n plus 2 system it should be other way around, it should be dis. Okay. So, this then you know how to. So, this is one side clockwise and this should be anti-clockwise. Now, you can. So, what it says, in one case methyl is up, this case also methyl is up. So, it is fine, both the methyls are in the same plane. So, see, you get a nice product, cyclized. Okay. Same thing if I take and do this reaction in light, what will happen under photolysis? Same compound, same triene system, this is triene, that is, so I am taking a triene system. So, I am taking a triene. Okay. Now, if I take this triene and photolyze this, so what the rule says? Yes, it should be con. So, con we know that it should be. So, one methyl will be up, in this case methyl will be down. So, you get two so your methyl will be, one case I have methyl up, methyl down. See, that's how it is nice. So, see, you can do not forget to do this, because this cyclization always happens. Okay. Then only you get this rearrangement. Just rotation is very important, but you should push this arrow to do the cyclization. So, this is under heat and this is on photolysis, see, which is exactly reverse to your 4 electron system. In 4 electron system, on heating gives you con and photolysis is on dis, but for 4n plus 2 system, that is 6 electron system, in this case heating is dis and photolysis is con. Fine. So, if I do the, if I take the reverse one, that is, if I take this system, this is again a 6 electron system, but I will just change my. So, I have taken hydrogen here and methyl, just reversed it. Okay. Now, I just say heating, you know it is dis. In this case, you get just the reverse product. See, this product you got on photolysis. Okay. In this case, you get for heating. Same thing if I do. Hydrogen methyl and hydrogen methyl, and I do the photolysis here. So, it should be con rotated. So, con, you know, it should be both clockwise and both should be methyl down, methyl up. So, it should be the reverse product. Okay. So, you get the just the opposite of this, clear. So, this is for 6 electron system. So, you have seen the 4 electron system, that 4 electron system most of the time obeys your 4n system, Then we have seen 6 electron system where it is nothing but it is a 4n plus 2 system. So, 4n plus 2 system is just reverse of your 4n, right. Okay. Now, we will take another example where we will go for 8 electron system. Okay. So, we will do 8 electron system. Right. So, what happens if I take this and heat? So, what system is this? This is a 8 electron, okay. In what system it is based on Woodward Hoffmann, whether it is 4n or 4n plus 2. Yes, it is a 4n system. So, you know 4n system on heating gives you what? What mode of rotation you can expect? Yes, con, yeah. So, it is nice. So, it is a con rotation. So, this con rotation, you know, both should be clockwise. So, you get a product. Right. So, your methyl should be up in this case, hydrogen should be down, and in this case hydrogen should be up and methyl should be down. See. So, you get this product on con rotation, clear, and you can have, if you want, you can have your hydrogen here, right. Now, see, this is fine, 8 electron system. Now, you know it is an 8 electron system on thermolysis according to Woodward Hoffmann rule. Yes, it should go con rotation, and you did a both clockwise and you get this product. Now, you see this product. This product again can undergo some another electrocyclic reaction, because if you see what system is this now, 6 electron system. Yes, 6 electron system you have studied, 6 electron system, again this can undergo electrocyclic reaction, right. So, if I take this product, because you are doing heating condition, so it can keep on going on. So, this on heating, now what it is? So, it is a 4n plus 2 system. So, what is this? Heating, this is 4n system, right. Heating, you know, it is con. So, for 4n plus 2 system, it should be just the reverse. So, it should be this, right. Now, this rotatory, you can easily do the this rotatory, because you have studied that, it should be in the opposite direction. Just write the product as it is, then we will write the correct structure. Just for understanding, we will write, because so that we can have your methyl here, your hydrogen, your methyl, right. Now, if it is both, so your hydrogen should be same, see. Then you fix your double bond, because it is cyclized, okay. So, you have a, right. So, you get this product. How to write this? Because it cannot be, so how to write this properly? If you want to write this properly, so this is your 4 system, right. So, your hydrogen both should be in the same plane, fine. So, your methyl is in the opposite. So, see, nice, right. See, that's the important, because whenever you do a type of electrocyclic reaction, you also see the product, because most of the case what happens is products can undergo other type of electrocyclic reaction, because you will see that I will take some examples in biosynthesis where you undergo a 4n, then this 4n system can do other disrotatory, or even they can undergo sigmatropic reactions, which we have studied earlier. They can undergo Diels-Alder reaction. So, you should know like it is not the product, you should understand the product also, whether this product can undergo further any reactions. Okay, that is also very important. So, this is of 8 electron system. Now, you have seen 4 electron system, you have understood 6 electron system, you have understood 8 electron system. So, you know this your Woodward Hoffmann rule of 4n system can be applied and your 4n plus 2 system can be applied. 4n very clear, on heating gives you con, on photolysis gives you dis. 4n plus 2 on heating gives you dis and on photolysis gives you con, just the reverse. Okay. Any doubt up to this? Okay. So, if you do not have any doubt, then we will just go for this. All whatever we have seen so far is nothing but it is a ring closure reactions, right. All the mode of rotations or whatever we have seen is you are taking a open chain of olefin or alkene type of systems, dienes, polyenes, and they cyclizes. Okay. Now, we will go to an example where we will understand a ring opening. Okay. These are all ring closure. Now, what will happen if I take a system and do photolysis, which is a cyclic system, and then photolyze or thermolyze, then the ring open. Whether that ring opening also is stereo specific or it under, then you need any rule to understand them better. Okay. So, we will go to now ring electrocyclic ring opening systems. See, there are many ways to understand this ring opening. What happens is that if you count with respect to your pi system, that is your 4 electron system, which I will tell in detail. If you see the con rotation and dis rotation which you applied for your ring closure, okay, for ring opening it will be just the reverse. What I say is that first thing, the Woodward Hoffmann rules, okay, the rule for the con rotation, or dis rotation of a ring closing reaction, are different than for ring opening. Very important. Okay. So, the Woodward Hoffmann rule which you are used for con rotation or dis rotation, okay, for ring closure is just different for ring opening. How they are different? They are nothing but it is vice versa, just the opposite. Okay. So, what it says that if I have a ring opening system, then how I write it, number of electron system, if it is, I am counting with respect to pi, okay, 4n system, the mode, okay, con allowed thermal and photolysis. Okay. So, what we have studied for 4n system for a ring closure, what you have studied 4n system ring closure, con it is allowed in thermal, right, but it is not, it is just the opposite, okay, but it is allowed in photolysis for 4n system. Okay. For that is 4L, but for this it should be other way round, just the opposite for your ring closure. For your 4n plus 2 system, it should be, okay, sorry, the con, okay, should be allowed in heating, photolysis not, 4n plus 2, this Okay. See, this is, I am just taking the one earlier one for this is for ring closure, okay, and this is for ring opening. You see, they are exactly reverse. Fine. So, they are exactly reverse. So, that is what I am saying. Electrocyclic ring opening, okay, follows different compared to electrocyclic ring closure with respect to con rotation and dis rotation, and they are different. That means in which way they are just exactly vice versa. That is all. Clear? Now, we will see the example and we will try to understand how it works. Methyl hydrogen, heating, con rotatory. Okay, heating. Now, what system it is? See, there are many ways of looking into it. See, if you are going to involve this, okay, then it becomes a 4n system. If I am not going to involve this, I am going to just count with respect to my pi electron system, then what system it is? It is just like your 4n plus 2, right. I am not going to involve this guy, I am just going to see with respect to this. So, then it is 4n plus 2. So, 4n plus 2, what the rule says for you? 4n plus 2 on heating, it is con, right. Yes. So, then I have a con rotatory. So, you have a con rotation there, just fine. So, then what you get? Because it is con, right, both should be same direction. So, I have an hydrogen here, I have a methyl here, I have a hydrogen here, I have my methyl here. Clear? This is for con rotatory. Any doubt? See, I am just considering this pi system only. For me, it is 4n plus 2 system, because I am not including this one. Okay, but anyhow, these electrons are involved to form this pi system, that is different. But for just the rule application, I am just saying that this is a 4n plus 2 system where I have included only one pi system, that is 2 electron system for me. It looks like 2 electron system, and for my rule says it is reverse. So, heating, then it becomes a con rotatory, I get this product. Same way, if I take this, okay, you have a hydrogen here, you have a methyl here, just the reverse product of this. If I take this and do it in heating, in con rotatory, okay, so I should get the other product. Like this is easy, so I should get my ZZ, ZZ. So, it should be EZ, yeah, this side EZ, and this should be my ZZ. So, I get this products. Clear? Any doubt with electrocyclic ring opening? This is for 4 electron system, like a system where I have 4n, I have used my 4n plus 2, because I have considered only this pi system. See, you can involve this guys, okay, and then you can use it as a con rotatory, that also works, but this is ideal for this type. Clear? Because this should be con rotatory. Fine. Now, we will take another example where you have phenyl, methyl, okay, I am taking this. Now, I am photolyzing this. So, what system it is? I am saying that you have to consider only this one. So, it is 4n system, okay, for me, because 2 electrons are involved. So, it is 4 electron system for me right now. See, you should not go for this, okay, just consider this 4 electron system. Okay. Now what happens, 4 electron on photolysis, what the rule says for you? Yes, this, get a this. So then, see, that is easy way of understanding it, and it gets right most of the time. Phenyl, you have a phenyl here, hydrogen, and you have a methyl, right. So, if I take similar system like with phenyl, phenyl, have a methyl, have a methyl here. Okay. Now I photolyze this one. Again, it is this, but I get the exactly the different product of this. Phenyl, get phenyl, I get the reverse hydrogen and I methyl. Fine. So that's, these are the some good examples of your ring opening system. Okay. So we have studied electrocyclic ring closure. There we have studied Woodward Hoffmann rule. We had your 4n and you have your 4n plus 2 system, and we said that on heating it is con allowed, photolysis, this, just the vice versa for that. And then we went for ring opening system, and we said that ring opening system will be just opposite, your Woodward Hoffmann rule will be just opposite for your ring closure system, but only I have to consider this electron system, that is your pi electron. I should not consider this one. So now this is your 4n system, then it should be just the reverse case. Clear? Any doubt? Because based on this only we are going to do some examples. Okay, these are very simple model, okay, by which you can understand this chemistry. Later, later we have to take it for some natural product synthesis and some biosynthesis type of molecules, and then we have to apply these rules and everything. Clear? Up to this, any doubt? Okay. Now we will go for one of the, we start with some simple synthesis molecules. Okay, we will see I've heard about this N-andric acid. Okay, if you consider synthesis of N-andric acid, okay, it's a cascade of pericyclic reaction. Okay, if you see their sequence of synthesis of several N-andric acids, it's a cascade of pericyclic reaction. I will just show one simple example, okay, where you can understand how this pericyclic reactions are involved. It's not only electrocyclic reactions. Okay, it's a cascade of pericyclic reactions. Clear? So we'll take one of the molecule. Oh, sorry. Okay. I have taken a system like this, okay, which has an alkyne and alkene in it. Okay. Now what I do is this: you do a reduction using your Lindahl catalyst. Fine. So you get a system like this. Okay. When you take this alkene unsaturated system, you do a reduction with your Lindahl catalyst, you get a system like this. So what is this guy? Tell me. Yeah, it's an 8 electron system. So that means it's a 4n So, you can use your Woodward Hoffmann rule of 4n. If I heat this, okay. So, what 4n system on heating, what it gives? Yes, con rotation, good. So, it will be con, I can get nicely this relation. So, I can get a, so that is all. Because it is one side out, okay, another side it should be in, right, and then you get this rearrangement, okay, this you know, this all you know. So, I have nitrogen here and then hydrogen here, clear, any doubt up to this. So, it is an 8 electron system, okay, and you know that 8 electron system, it is a 4n system, and on heating you know it undergoes a con rotatory. So, I did a just a con rotatory ring closure. So, I got this product. So, one, because you are changing, one should be out and one should be in. So, I have OH here with it. Any doubt in this? Okay. Now, tell me what will happen. I told you, like if you are seeing an electrocyclic reaction, okay, it is not that this is the product. You should see in such a way that whether it can undergo further any pericyclic reactions. Because in 8 electron system I showed you an example where it undergoes a further pericyclic reaction. See, in this case this can undergo a nice electrocyclic reaction, because what system is this? Again it is a 6 pi electron system, right. So, 6 pi electron system, nothing but 4n plus 2 rule. You have to use your 4n plus 2 rule. So, on heating what it says 4n plus 2 rule, because you know for 4 electron system, for 8 electron system it is 4n, on heating it is con. So, it should be other way around. So, it is this, fine, yes. Now, it can undergo a this. See, this type of, you can expect this type of questions in most of the cases. So, I have used my knowledge of my electrocyclic ring reactions and I have applied it. See, this is done, this type of anti-andric acids, it is a cascade of pericyclic reaction if you see their biosynthesis, and it is very nice. It undergoes a Lindahl, then it undergoes a, you can see both of your chemistry. You can see your 4n system ring closure, okay. At the same time you can see your 4n plus 2 ring closure. Heating, one gives you con specifically and another on this gives you specific this product. See, these are the beauty of electrocyclic reactions. Clear? Okay. Any doubt on this? Okay. Now, we will see then famous your known reaction, that is biosynthesis of vitamin D3. We can just see your biosynthesis of vitamin D3. Okay. So, what will take, so what is this? I will ask you, I will draw the structure, you let me know what is that. So, be careful with your stereochemistry when you are dealing with this type of systems. Your angular methyl all should be correct. Okay. So, what is this compound? Come on, man. Yeah, 7 dihydrocholesterol. Right, 7 dihydrocholesterol. So, I have taken this. Now, I say that I photolyze. This unphotolysis undergoes a nice 6 pi conrotatory, undergoes very nice 6 pi conrotatory. Okay, to give you have studied this very good electrocyclic reactions, which then you have okay, clear. Now you have your methyl, then you have your system. See, it's a nice ring opening. It's a very good ring opening process. Okay, nice ring opening. Unfortunately, it's a 6 pi electron system, conrotatory. If you just take 7-diirocholesterol and you photolize this, you get this. What is this? This is nothing but pre-vitamin D3, initial step to your vitamin. No? It's a pre-vitamin D3. Have you studied now what will happen? Because in one class I have taught you what will happen to this vitamin D3. See, I told you that why. Now you have to understand this. Not in just, you should not understand with respect to electrocyclic reaction, you have to understand the whole as a pericyclic type of reactions. Now see this product. Now is there is any possibility this can do under light? I can give you, it can be a type of sigmatropic shift. Any idea? Yes, nice. It should be 1,7 hydrogen shift. You can it undergoes nice 1,7 hydrogen shift, because you have this methyl, you have this proton. Okay, it can undergo 1, 2, 3, 4, 5, 6, 7. Can easily undergo 1,7 hydrogen shift to give you vitamin D3. Get your vitamin D3. See, so you have studied that your first step is nothing but an electrocyclic ring opening and photolysis 6 pi electron system conrotatory. Then you have studied, you included your knowledge of sigmatropic reaction where it undergoes 1,7 hydrogen shift. So you have taken 7-diirocholesterol and you get you vitamin D3. Nice biosynthesis type of molecules. Let's see one more nice examples. This you heard about. I think you have studied about this biosynthesis of, because you have that class on biosynthesis, right? So you have studied about biosynthesis of aromatine. It's nothing but it's a naturally occurring. What is this? Aromatine. It's a naturally occurring oxypine, right? So it follows a number of reactions. Okay, it follows initial epoxidation and it goes on. So I just we will concentrate only on one step, that is your where it undergoes an electrocyclic reaction. Okay, so I am taking only that particular step. So I can have an epoxide. Okay. Carbonyl, R, and then you can have R prime. I can have a disulfide linkage here. Okay, so you have a system like this. Now this on heating, what you can expect? This system on heating. What system is this? Yeah, you have pi system, so it is heating, it is rotatory. Very good. Yeah, same your rule knowledge. So it's a disrotatory, that's fine. So very good electrocyclic ring opening reaction to give you a nice product. It is NR, okay, sorry, this should be NR prime, should be NR prime, NR prime, okay. This doesn't matter for you much, but the idea is that it undergoes a nice electrocyclic ring opening reactions on heating, disrotatory. It's one of the important step in your biosynthesis of aromatic, okay. So like that there are many in natural product synthesis you can see it uses lot of pericyclic reactions, okay. Electrocyclic ring opening, electrocyclic ring closure, then sigmatropic shift followed by, and you get a nice natural products reactions, okay. Fine. Let's see another nice synthesis of natural products. So, I am concentrating, I am not explaining you more about the natural product synthesis. I am just taking the crucial steps of electrocyclic reaction and pericyclic reactions which are involved in that natural product, and we are discussing that, okay. The other steps which are involved, you should refer them. Okay, I have a system like this. Now what happens if I heat this? I take this system, now I heat it. So what do you expect? Yeah, now you have to write by yourself, right? Because this one heating, I can think this as a my system, right? Any idea? Which you have studied. If you just think this alone, it should be like this, right? This whole part should be like this, which we have studied, right? So it should be electrocyclic ring opening. It should be a conrotatory. Just now only we have studied that example. Yeah, just system like this. Okay, so same system it is. I studied. So what will happen now if the breaks? Because a ring opening system, so I can push this. It's a nice electrocyclic ring opening happens here. So giving me my system here. OH. Okay, you get this product. Fine. Any doubt? That's good. Now, what you can expect? One, it should be easy. Yes. Again, you can have a ring closure here, right? You can push this. You can have a nice ring closure. So you have an O methoxy. So I can have my me. See, be careful with the stereochemistry. See, you get this nice product. So you can that's what I am saying, like there are several examples by which you can understand this electrocyclic reactions, like so it's not about only you have to think about electrocyclic, you have to think all your combinations of pericyclic reactions, and if you apply them together you can see many biosynthesis in this way, and natural product synthesis you can do one step pericyclic ring closure, another step Diels-Alder reaction, sigmatropic, and there are many quite number of examples which you have to do and get practiced. Okay, but basically there are certain rules which you have to follow, which you know, that Woodward Hoffmann rule. Okay, a 4n system, what you should do, 4n plus 2 system, how it should ring closure, just opposite how we should ring open for 4n system and 4n plus 2 system, and based on that idea you should apply for your other chemistry part. Okay, any doubt up to this? No, that's good. So what we will do is that in the next class we will try to understand the other examples. Okay, I did some quite good examples of natural biosynthesis. In other case we will try to understand about azulene or aniline type of electrocyclic reactions. They are much more interesting. Okay, so we will see you in the next class. Thanks.